Hey everybody, let's talk about equilibrium today and figure out what that means. Starting with a definition. When a system reaches equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So if we have a chemical system, let's say we have chemical A, and it is going to react to form chemical B. Well, the reverse reaction can also happen. Chemical B can react to form chemical A. So when the rate of the forward reaction and the rate of that reverse reaction happen to be equal, we're going to see two things happen. One, if we're looking from the outside, we are going to see that the concentration stops changing. However, it's really important to note that the reaction continues. So that's what equilibrium is. And many chemical processes will establish an equilibrium. So how can you tell when equilibrium is reached? Remember I said that when we're at equilibrium, the concentrations will stop changing. So if I look at this particular example, so I've got 3A plus B making 2C. If I look at the concentration of A, I'll see that it goes from 1 to 0.7 to 0.43 to 0.34, but then it's at 0.34, 0.34, 0.34. So we know that once we have reached 3 minutes, equilibrium has been reached. And for the rest of this time, this system is in equilibrium. The concentrations are no longer changing. We can look at any of the chemical concentrations and you will find that all of their concentrations stop changing at the same time. So let's complete this table. Between 0 and 1 minute, A changes by negative 0.30. So B's change will be 1/3 as much. So I'm going to have minus 0.1. That means after 1 minute, I'll have 0.30 molar in B. And then for C, it has a coefficient of 2. And so the change will be plus 0.2. And so after 1 minute, I'll have 0.2. If I look at the next minute, I see that the change in A is minus 0.27. And so the change in B will be minus 0.09, 1/3 as much of A. And then the change for C will be 2/3, so plus 0.18. And so that means that at 2 minutes, the concentrations are 0.21 and 0.38 for B and C respectively. Going from the second minute to the third minute, I see that my change for A was minus 0.09. And so that's going to make the change in B 1/3 that amount, so minus 0.03. And then the change in C twice that amount, so plus 0.06. And that means that what I have after 3 minutes is 0.18 molar for B and 0.44 molar for C. But now from here on out, we see that the change for A is 0. Which means the change in everything else is going to be 0, 0. And these concentrations are going to remain constant. And again, we see for all of the chemicals involved in a reaction that once equilibrium is reached, their concentrations stop changing. So at equilibrium, even though the reaction continues, we no longer perceive a change in concentration. So how can we make this more useful? People did a bunch of experiments with a variety of systems that come to equilibrium. One of those is the equilibrium between dinitrogen tetraoxide, which is a colorless gas, and nitrogen dioxide, which is a brown gas. And so someone at one point put in a whole bunch of different initial concentrations of both the reactant and the product. So when we're talking reactant and product with equilibrium, we really just mean left side and right side of the equation. So they put in different quantities of those chemicals and then measured what their concentrations were when those concentrations stopped changing once equilibrium was reached. And then they started looking for relationships. And you'll notice that if what you're looking at is just a straight ratio of the product, as we have it written, NO2 over N2O4, that ratio is all over the place. But if you take and make a special kind of ratio right here, where you take the concentration of NO2 and you square it, and then you divide that by the concentration of N2O4, you always get the same number. And people did this for a variety of different materials. And they found that there's this special ratio that will always give you the same value for a particular reaction. And that leads us to what's called the law of mass action. The law of mass action says that for a reaction at equilibrium, and that has at a particular temperature, there's a ratio of products to reactants that's going to be a constant. For a generic equation, if I have AA plus BB in equilibrium with CC plus DD, where the capital letters are the chemicals themselves and the lowercase letters are whatever their coefficients are. In the chemical equation, there's a ratio that's a constant. We're going to use K for what's called our equilibrium constant. And that ratio is products on top, the concentration, or we'll see pressure here in just a minute, but the concentration of each of the products raised to their coefficient divided by the concentration of the reactants raised to their coefficient. That value is always a constant at a particular temperature for a reaction and is known as its equilibrium constant. If the value for K, that equilibrium constant, is greater than 1, we're going to have a larger numerator than denominator, and so we're going to have more products than we have reactants with this ratio going on at equilibrium. If, on the other hand, K is less than 1, we're going to have more of our reactants. And if K is equal to 1, we're going to have equal amounts. Now recognize this also does have to take into account what those coefficients are. But the idea that if K is greater than 1, your products are favored. If K is less than 1, your reactants are favored. And if K is right about 1, you have equal amounts is going to be a really important one for us. So we can write equilibrium expressions and equilibrium constant expressions in terms of either concentration or pressure. And so we're going to write one of each here. If we look at the upper equation I have written, we have HCOOH, which is an aqueous solution reacting to form a hydrogen ion and HCOO minus. So that's formic acid reacting to form a hydrogen ion and the formate ion. Obviously, there's no gases here, so it makes more sense to talk in terms of concentration. And so we're going to write a Kc expression where I will write the concentration of my products over the concentration of my reactants raised to their coefficients. Well, in this case, all their coefficients are 1. And I'm going to remind you that those square brackets, that means concentration. So how many moles we have per liter. Similarly, we can write an equilibrium constant expression for a gas. Okay, for a gas, we could use concentration because we have moles of the particle in a particular number of liters of that gaseous container. We can also talk about it in terms of pressure, which can be more convenient to measure for a gas. So I can write a Kp expression where I have the pressure of the CO, which is going to be squared because its coefficient is 2, times the pressure of the O2, products over reactants. So the pressure of the CO2, which is going to be squared because its coefficient is a 2. So just remember, when you go to write an equilibrium constant expression, products over reactants, use your coefficients as the exponents that you're raising either your concentration or your pressure to. We can categorize our equilibrium processes either as homogeneous equilibria or heterogeneous equilibria. As you would kind of deduce from the prefixes, in a homogeneous equilibrium situation, the phase of all the reacting materials is the same. And so we'll see all aqueous solutions are all gases here. For a heterogeneous equilibrium, not all the reacting species are in the same phase. And so we have to toss in a caveat. When we're writing equilibria constant expressions, when we're determining those equilibrium constants, solids and liquids are not included in the equilibrium constants or in the equilibrium constant expressions. Let's do one example just to make sure this made sense. So I've got a reaction written down here at the bottom where I've got solid iodine reacting with aqueous chloride ions to form chlorine gas and iodide ions. And so when I go to write my Kc expression, products over reactants, my chlorine is a gas. I'm going to use, like I said, a concentration because this is a Kc. I'm going to make a point to include the coefficient next to the iodine, which is a 2, as an exponent in that equilibrium constant expression. And then for the reactants on the bottom, I'm not going to write I2 because that's a solid. I'll just write the chloride ions. So it turns out that Kc and Kp are related to one another. So if you have the same equilibrium and you have a choice for how you're going to write it, either as in terms of concentrations or in terms of pressure, you're going to get different numbers. But it's the same equation, so there must be some relationship between those two values, and it turns out there is, and it has to do with how many moles of gas are in your reaction, both products and reactants. So let's take a look at a generic expression again. So to keep things simple, we have A turning into B. These are both gases, so I could choose to write either a equilibrium constant in terms of concentration, how many moles of gas we have per liter of that gas, or in terms of pressure. And when we're writing Kp expressions, our pressures are going to be in atmospheres. So how do we relate these two to one another? We're going to use the ideal gas law. So I know you saw the ideal gas law last year. We haven't seen it yet this year, but I'm going to remind you that the ideal gas law says that for a particular gas, its pressure is going to be, depending on the number of particles, a constant, the temperature that you're at, and the volume that your gas is occupying. Well, look carefully. The number of particles over a volume in liters, that's concentration. And so what I can do is I can write my Kp expression in terms of the ideal gas law and then tease out the equilibrium constant in terms of concentration out of that. So I'm going to derive this for you right now. And a derivation is just a mathematical manipulation of an equation or of a relationship. So all I've done so far is I have written my Kp expression in terms of the ideal gas law, saying the pressure of B is the moles over the volume times RT. And then I've separated that term into two pieces, into a concentration component, and then kept the ideal gas constant and the temperature as a separate term, but they're multiplied together. And then I further combined the RT, since on the top and the bottom, by the rules of the way exponents work, that's the same thing as having RT raised to the B minus A power, because A is in the denominator. And if you look, this right here is your Kc expression. And so what we have basically said is that Kp is equal to your Kc times RT, and then B minus A. B was the moles of gas I had on the products, the little b. Little a was the number of moles of gas I had on the reactants. And so this term, B minus A, is my change in moles of gas, looking from the product side to the reactant side, and I'm going to call that delta N, which is the moles of the product gas minus the moles of the reactant gas. So there is a mathematical relationship between Kp and Kc. If there's no change in the total number of moles of gas you have, they'll be the same. But otherwise, there is a scaling factor that has to be taken into account. More often than not, we're going to work either with Kp or with Kc, but I do need you to understand that mathematically, the numbers for those equilibrium constants will be different, and we can switch back and forth between them. I know there's been a lot going on so far, but we've got one last thing we need to focus on when it comes to our equilibrium constant expressions. It turns out that because of how we write equilibrium constant expressions, products over reactants raised to their coefficients, if we change the way we write a reaction, it's going to change the value for K. So let's take this one as an example, which was dinitrogen tetroxide reacting to form nitrogen dioxide. For this reaction, I can write a Kc expression, which will be the concentration of the nitrogen dioxide squared over the concentration of the dinitrogen tetroxide. Well, what if I were to flip that equation? It turns out if you reverse a reaction, because it's products over reactants, you're going to take the inverse of your original Kc value. So if you were to reverse that reaction, you have to take the inverse of K. Whatever its value was before, 1 over that will be the new value for your equilibrium constant. What if instead I multiply through by a coefficient? Well, if I take a look at this one, since I have doubled all the coefficients, all of my exponents have changed as well. And so it turns out that what I'm doing here is I'm taking the original value for the equilibrium constant and I'm raising it to the exponent that was my coefficient. One more situation we have to look at is what happens, like we were doing in Hess's law, if we add two equations together. What is that going to do to my equilibrium constants for the overall process? So if this is my multi-step process, I'm going to back this off to a generic so that it's easier to see what's going on. We have A and B making C and D, and then C and D makes E and F. I have equilibrium constants written for equilibrium constant expressions written for each of the processes. If I look at what the overall process is here, and at what its equilibrium constant would look like, and then look back up at those individual equilibrium constants for each step, I will find that my overall equilibrium constant is the product of each step. And this finding generalizes to more steps, to having coefficients. Your overall process will have an equilibrium constant that is equal to the product of all the individual steps in that process.